a lot for giving me again the opportunity to speak. So today, first there will be some, last time was mostly things which are not due to me or my collaborators. Today there will be some original work, and so I should list my collaborators here. So this is what I will tell is based on several collaborations. So the main theme is by a collaboration with Slava Krushkal. I should learn the alphabet. So Sergei Gukov, Slava Krushkal, and Dupay. This will be the bit which actually has something to do with theta function, but it's also in the background based on work with Tilman Bauer on topological Jacobi forms, or I should say Tilman Bauer and Mayuko Yamashita. And there's also, I will use some stuff about Equivariant TMF, and this will be based on the joint work with David Gardner. So, long list of people. Okay, so start with some recollections. And so we had the opportunity to look at quadratic forms on Z to the D, which I use this notation, and also at bilinear forms on Z to the D, and I explained how this embeds, and I will always use the letter Q for quadratic form, and then I have here BQ, associate bilinear form. And then we had these theta functions. So theta q was a certain modular form of weight d half if q is positive definite plus unimodular. And then there was also this other theta function, theta q, which was a certain Jacobi form, weight d half, and this had this index. It also depended on the index, which is a bilinear form. And then let me also recall what we actually wanted to do with this, namely, so and the goal is actually associate to every unimodular the bilinear form class TV in the homotopy groups of TMF, and ideally this should be related to theta q if B equals BQ, and we wanted to do this by topological Jacobi forms. So this was what I sketched at the very end, that we wanted to, in some sense, the idea is to produce this TV to find an analog of this theta function Jacobi form, not a modular form, in some version of topological Jacobi forms, and then restrict back to TMF. So this is the goal. So what I first have to tell you is what topological Jacobi forms are. And I will first give a definition which is has no apparent relationship to what I told you yesterday about Jacobi forms. And then, if time remains, I will connect. So so topological, or TJF, abbreviate via twisted equivariant here. So before I explain anything about twisted equivariant TMF, I want to recall a few things about twisting in general, because while not strictly necessary to do this, I think it's something good to know, and maybe not everybody knows. So let's say non-equivariant. Twist. So let R be an infinity ring spectrum. And X be a space. And let's say it maps to pick R. So this is the data of a twisting. So what is pick R? So it's also a space. So by the homotopy hypothesis, we know we can also view space as an infinity groupoid. So this is just the full. It's a subcategory of R modules, namely the subcategory of invertible R modules, and we only consider equivalences between invertible R modules. Because only consider equivalence, not all morphisms. It's an infinity groupoid and hence a space. And this is the data of a twisting. Okay, then define F, the F twisted R cohomology as a star of Fx, which is defined to be the limit of x of f. So why is this a good definition? Well, first example, or maybe it's example 0, is that f is constantly just an n-fold shift of R. It's the easiest functor to Picard groupoid you can consider. Then this limit, then R of f of x is the limit over a constant thing. And this is just Rn to the x. So this is the cotensoring of R modules over spaces exactly by, take this thing and take the limit over the constant diagram. So in models of spectra, this is usually realized by taking on each level of the spectrum the mapping space from x to the, let's say, the kth space in this. And then we know that if we take pi 0, this is exactly the usual nth cohomology of x. Okay. Any questions about this? So then another example, which will be relevant for me today, but I think it's good if one wants to get a handle on these things, these ideas. You can look at R equals hz. Then, well, the Picard groupoid hz, Picard infinity group of hg is pretty simple, because the homotopy groups of the, it turns out the homotopy groups of this Picard groupoid are at pi 0, we have the Picard group, so isomorphism class of invertible modules. And then the higher homotopy groups are just a shift of the homotopy groups of the ring spectrum itself. So the lowest homotopy group here is just, I have, let's say, my star of this is, I have a z in degree 0, because these are just the shifts of hz, there are no other invertible modules. And then I have a z mod 2, or rather I should say plus minus 1, here, which are the units of z, of pi 0 of this. And then I have a shift of all the other homotopy groups of hg, which happen to be 0. So this infinity groupoid is just a usual groupoid. And then a map to this is exactly what's called a kind of a local coefficient system. So for each point in X, we have a copy, something which is isomorphic to Z, but not canonically isomorphic, and if we have path, then we have an isomorphism between these copies of Z. Because it's an actual groupoid or an infinity groupoid, this will factor over the fundamental groupoid, and if X connected over the fundamental group, which is the more classical notion. And then you get a cohomology with local coefficients. Which, for example, figures in the Serre spectral sequence. Okay. Then let's come to an example which is actually more relevant, at least spiritually, for what I want to say. Namely, say we want to do this in the case of R equals TMF. I mean, the same formal picture applies, but the problem is that this Picard infinity groupoid, Picard space, think of TMF is terribly complicated, and it's not so easy to understand. Certainly not a priori, and even like all we know, it's not so easy, but luckily there's a map from a much simpler space into it. So first of all, we know that I have a unit map from the Picard space of the sphere into the Picard space of TMF. If a map from sphere to TMF, I can just tensor up. And then I know that I have the J homomorphism. So for each, comes essentially from each vector space, I can take one point computation, take suspension spectrum. This is some suspension of the sphere, so an invertible mod. And then this happens to factor to the fourth Postnikov stage. So why is this? So this is actually a pretty deep theorem. It comes from the fact that so the fiber of this thing, of this map, is what's called BO8, because I mean there are no homotopy groups between the 4th and the 8th of BO, so B strings. And it turns out that this thing is null, and you can use it to show that then this factors over this. So why is this null? I mean, this is a pretty difficult theorem, which is essentially equivalent to the existence of a map from the string Bordosian group, so the Tom spectrum for this, to TMF. It's this Andrew Hopkins-Resk string orientation. From this we get this map. So this means as soon as we now have a map from X to this fourth Postnikov stage, then we can twist TMF by it. So that's very convenient. It was a much easier space. In particular, if you give me a 4, I mean, I think I mentioned last time that KZ4 maps to this, so if you get a map to KZ4, fourth cohomology class of X, I can twist TMF by it. Okay, any questions about this? So before I can twist equivariant TMF, I should say something about equivariant TMF. So there exists globally equivariant refinement of TMF. So if you're not into globally equivariant yet, this means in particular, and this will be enough for us, the excess G spectra. Like this, and I mean, they're all infinity rings. And before somebody asks, they are known to be E infinity in the naive sense, and one expects them to be E infinity in a stronger sense. And actually there has been some very interesting work in this direction due to William Bardarama and Jack Davis, and I think Zielinski is also involved, still unpublished, but they, oh, this is what I want to do. So, and they construct some of the norms, but it's still work in progress. Okay, and we have this C spectra, and This kind of things are due to a number of people, still alphabet problems. Okay, there's so if you want to have the global story, there's a paper by David Gabner, Selinsky, and Luca Pohl, who might be in the audience, yes, who established this, and this is built on non-global work earlier. Well, it's a bit of a complicated history, but so there's this famous survey of elliptic homology to Louis, which like 2007, and there he sketched roughly how to do this, or at least to get a G-equivalent homology theory, and then David Gabner and myself elaborated on this, providing many details, and then these guys further built this into a globally equivariant space. I should also say, even like the work of Louis was based on like this much earlier work. Grojnowski and actually like John has a very nice paper on rational equivariant elliptic homology and so on. Okay. So I don't want to twist very complicated spaces X in this case. I mean, of course, I should not really twist spaces, but I should twist the equivariant TMF homology of a G space. But the only G space I want to do it for is the point, which may be my favorite G space. So this will be enough for our purposes. And and then it's a conjecture which says informally. So one can twist TMFG by maps from BG to the Postnikov stage of BO. So what is partially wasted? Okay, but they're still there. So what you can get quite easily from this, like say you want to take the Borel equivariant TMF of a point, say, which is just TMF of BG. This you can twist by such a map. But maybe, which is not so clear, I mean, what's certainly not clear, maybe not clear why one should expect it, that one can also twist equivariant TMF, genuine equivariant TMF. So more precisely, I should say, one may conjecture that, so one has G fixed points of BOG. There's also J homomorphism, which goes to the Picard space of TMFG. And whether I put G fixed points here or not depends on what you mean by Picard space. I would mean like a classical Picard space, not like a G equivariant space here. And then you might conjecture that this factors. So there's some evidence that this is true, but maybe I first write down what this means on the. I mean, this is like often hard to really establish such factorization of a map of spaces. It's much easier to do it on a level of sets where you take pi 0. So let's discuss the pi 0 level statement. So, and let me not, I mean, this somehow restricts to things of virtual dimension 0. Let me ignore this a bit. And essentially pi 0 of this is ROG. And so I can go to the Picard group of TMFG. And I forgot, lost my color. So if I have some virtual representation V, this will go to TMFG to the SV, so the SV being the 1-point complication. And then, well, I can go to perhaps this defines, if I have a representation, this always defines a virtual vector bundle on BG, and I can go further. Okay, and this is what we are asking for. And so regarding evidence, well, I mean, there's a general evidence that this has something to do with twisting. And then ideally, this should come from some equivariant version of the string orientation. But no one proved this, or, I mean, even like the precise formulation is a bit, I mean, one can formulate something, but it's not quite, a priori not clear what the correct formulation is, because you have to give the correct version of the equivariant string bordism. And for this, you have to decide what is equivariant B string. And ideally, there should be like some theory, like if you have a Lie-2 group and you can get some classifying space out of this. And I think in principle this exists, and this has to be kind of compared to some other versions you might come up with, then hopefully this conjecture would arise naturally. And I should also mention, so people with physics allergy, kind of please don't listen. So I had before that that there was a certain mysterious concept of anomaly of a quantum field theory, which kind of played a role that you can get the degrees of the TMF class of this. Pi d, kind of anomaly D would correspond to pi d of TMF. Turns out for G equivariant quantum field theories, there's also a notion of anomaly which is generally accepted to be classified exactly by this. So this would be like, in some sense, a natural kind of analog of a degree of a G equivariant TMF class. So exactly, I mean, in some sense, a twist of the cohomology of a point is called degree, and this would then happen. Okay. So this is like more like I can also use these backboards. So this is more like philosophical evidence, but there's also a further piece of evidence, the theorem that this exists if G is a torus, and also in some other cases which are not so relevant right now, and the other cases are partially joined with Mayuko Yamashita.
You have a single star and a double star.
Yeah, it's not important, exactly, thanks. So, and I should also say, in the case, I mean, in the case that G is a torus, it turns out that this map here is surjective. So this factorization is not a construction, it's a property. So this means that I have told you what this arrow is in the case of a torus, namely it's a unique factorization if it exists. I mean, there is the equivariant TMF, there is an analog of a TS-Siegel completion, but it's a bit involved. The sense that, so as I will explain later, the natural setting of like torus, say, circle equivariant TMF would be look at sheaves on the universal elliptic curve. And if we really pass to something like this, then we would always have to take global sections of this. On the level of global section, there's no TS-Siegel completion. But on the level of sheaves, there is one where you have to complete at the zero section of the universal elliptic curve. But generally speaking, the genuine theories are easier to work with in a sense than the Borel theories, in some senses. And actually, in some sense, I would also try to avoid using the Andrew-Hopkins-Resk theorem because, I mean, the proof is very difficult, and in principle, there should be a more conceptual proof using equivariant TMF. And yeah, but it's a longer story. Now I lost also my white chalk. There it is. Okay. And maybe a bit funnily, the case of G at torus actually uses the case of G equals SUN. which may be a bit surprising. But it turns out that this Picard space is easier in the case of SUN than in the case of towers. And I should also make a comment. There's a precise statement. If you really want to formulate like this, I have to use a theorem which I think, another result which I think is also true, but I have not fully established. I make a certain identification here, which is not necessary for what I want to tell later, but simplifies the story a bit. Okay, now recall that in the case, so let's G now be a torus. It's my favorite notation for a torus. So let's say T is the circle. Then I mentioned last time that this thing here is isomorphic. And then we make the following definition. And then maybe I should also give this thing a name. That's called TW for twisting. Definition, and this is to Lennart Meier, also discussed with Mayuko Yamashita. We define TJFB for some B bilinear form as the as we take this, we identify B with an element here. We take this thing to get an invertible TMF module, and then we take the fixed points. So this is it. In the Picard group, TMF TD. So this is my definition of topologically equivalent. Should do this. So this is my definition of topologically Jacobi forms as twisted torus equivariant TMF. So as I said, there's no apparent relation to Jacobi forms.
What does the superscript T to the D mean?
Fixed points. And I should tell you next what the relationship.
What is the fixed points of the point?
Point? So I mean this
TWB is an element
of the Picard group, but I view this as an invertible module over TMFG. And this is a G spectrum, and then I can take a TD spectrum, and then can take fixed points. Further questions about this definition? Except for the question what it has to do with Jacobi forms. Apparently not. Okay.
So is it clear that this is invertible as a non-equivalent? Because I think that's...
Certainly it's not. Certainly it's not. So what we will see later is that if B is unimodular, then it will be invertible as a TMF module, and hence a suspension of TMF. But if B is not unimodular, so essentially, I mean, this doesn't quite make sense, but there's like, I guess it makes sense if you were complexified, then you could say like it's a, I think if you complexify this, it will always be a free TMF module, a certain rank, which depends on the determinant of the representing matrix. Actually, this is actually like what happens in my paper and program with Lennart Meier. So if you look at one-dimensional bilinear forms, so essentially a number, then we give an explicit finite complex you can smash TMF with to get these things, which is related to CPN. There's certain modification.
It's just a matter of suspensions, I guess. But you took V in ROG, which would maybe correspond to Z plus BO instead of BO.
Yes. And but I mean the Z comes kind of for free. I mean it's important to add it to make a correct statement. But I mean this is just the degree shift. And so this part I don't need here of the degree shift. I should also add, so these won't be ring spectra, because there's no reason to, because these are just, this thing is just a module over T maps. So one would expect if you take the direct sum of all of them, then this is of a fixed, for fixed D, this becomes a ring spectrum, or even better, it should be like a graded, highly structured ring spectrum, but with only partial results in this direction. So, if there are no further questions, then let me try to relate this to Jacobi forms. And I will take the opportunity also to say you a little bit about how equivariant TMF works, because if one doesn't, then one cannot. Relation to Jacobi forms. And first of all, also how does equivariant TMF work? So I will only tell a small part of the story, because otherwise this would be at least a full talk. First of all, I want to say what the central player is. And the central player is E, which is the universal elliptic curve. Over the moduli stack of elliptic curves. So, so the moduli stack of elliptic curve represents the functor of taking elliptic curves over something, and there's a universal object which is, so to speak, classified by the identity ML to ML. So an elliptic curve over the moduli stack of elliptic curve kind of exists for formal reasons. And to make this more concrete, and actually for later purposes, let me say how this looks like over the complex numbers. So, so last time I told that over the complex numbers, there's some sense, at least if you like this kind of stuff, there's a more concrete version of the moduli stack of elliptic curves where you say, oh, we have an SL2Z action where Möbius transformation on the upper half plane, and we take this quotient. So, and the corresponding was that we have some t in h, this tau on h. This corresponds to the elliptic curve e tau, which is c divided by z times 1 times z times tau. This kind of letter. So what we now do is we look at something slightly more complicated, namely we look at h times c, and we quotient by SL2Z semi-direct product z squared. So where z squared acts on c just by z squared is a subgroup of c by translation, and the semi-direct product is by the natural action of SL2Z on z squared. And this maps by just forgetting the last coordinate, h SL2Z. And it turns out that when I take a point here, some tau, and the fiber exactly e tau, because I kind of remove the first coordinate here, and I have just c modulo z squared, and but because I have the fiber tau by this action, if you work this out, it's not the standard embedding in C anymore, but it will be this kind of embedding when I get exactly. So this motivates why this is the complexified universal elliptic curve, because over each point of the moduli of elliptic curves, I have exactly the fiber being the corresponding elliptic curve. Okay. Now, there's a very nice construction due to Louis that there is also the sheaf out of E of E infinity ring spectra on this E, so such that pi 0 is a classical structure sheaf. So this is in his elliptic homology 2, where he gives, I mean, in some sense he doesn't start with a classical stack and then construct a sheaf of E infinity ring spectra, but directly sees that this conjunction of E comma this has some universal property, and he constructs it by an existence theorem that something satisfies this universal property. And then by a very lengthy and difficult analysis, he can actually relate this to the classical modular problem. Okay. So actually, you can also repeat this. So if you look at so on, you can take E tensor z to the d, or more concretely, you can look at the fiber product of E. So E lives over ML, and we can take the default product. So you should think of this as the default product of E. So we want to make sure that the fiber, of this over ML will be a default product of an elliptic curve. So that's why we take this fiber product. So there's also a sheaf of E infinity rings. O top. Okay. And once you have this, this is rather form. Okay, so how do we define now equivariant TMF? As I said, I want to only tell you a small part of the story, because it's only relevant for us to take equivariant TMF at a point, and it's only relevant for us for tori, not for more general groups. So we define the T fixed points of TMF T. So to speak, the T equivalent TMF of a point to be the global sections of our topic. Likewise, if we have higher dimensional tori, this is the global sections of this corresponding product. This can be calculated explicitly. This global section is actually equivalent to sum of shifts of TMF, but this is paper with David, but this may be not so relevant right now. But this is a definition one does. And this might sound pretty unmotivated, why one might do something like this. I mean, there's a long story to this, how this is like in some sense analogous to how it happens for equivariant K-theory in the background, but I don't think I want to get into this right now. So there are good reasons why we want to do it, and it works. We got a good theory. So now, the way one actually constructs this twist of towards equivariant TMF is to say, oh, I want to twist the structure sheaf here, and what does it mean to twist the structure sheaf? I should replace it by a line bundle. So, so this twist of some B will be global section of a certain invertible OTOP EZD module. OTOP B. And I say invertible module, but I mean this is also known as a line bundle, invertible module with structure sheet. And this is like this is what one actually defines. Okay. And it turns out that these line bundles are not completely new. I mean, they are new in this derived spectral setting, but we can go to a much more classical setting, and then they actually have been studied for, I mean, explicitly for decades and implicitly maybe since the 19th century. Namely, okay, so first of all, we can look at this. It's now a line bundle. Call this LB. Now a line bundle. This thing. And then we can even go further and we can complexify. We get a line bundle. On complexified guy. And above I gave the formula for the case where d equals 1, so I just have this thing. There's actually a more general formula where you say it's h cos c to the d. So do c squared. So, how does it help us? Now we transport ourselves back to Tuesday and we call what a Jacobi form was. Sorry?
I'm worried you were going to say the 1820s.
My time machines are not so strong yet. Okay. So, what was a Jacobi form? So the Jacobi form were where I have weight k index p. Were functions from h cos c to the d to c satisfying certain transformation behavior with respect to the SL2 z d squared, the d action. On this thing. Just a little bit more. And this transformation behavior depends on the weight in the index. And let's call this LBC. And so I already mentioned the context of modular forms. You can translate that a function satisfies a certain transformation behavior in saying that's a certain section of a certain line bundle on this. And no surprise now, it's the same as holomorphic sections of LBC. And then we have to, for the weight, we also have to tensor certain other line bundle on this guy. So, and so what is the upshot of this whole discussion? Okay. So say we have now p phi to k of TGFB. So it's the same as pi to k of the global sections then there's always, if you have global sections of some sheaf, there's some descent vector sequence which comes to an edge homomorphism. So this goes, there's an edge homomorphism, which goes to where? Well, it goes to H0 on E, ZD. And then I have here pi 2k, LB top. And this is LB. And then I have to still tensor with omega to the k to get the correct degree. Let's call this Jacobi forms.
What is L top LC or?
Sorry, what?
What is L upper top LC or?
L top B is this. So I have three different levels. Sorry, it's a bit confusing maybe. There's a spectral level. It's a top on the top, and there's like I can take pi 0, then I get something on the integral moduli stacks. Then I have no superscript, and then I complexify, and then I have a C. And then I can go further to, let's call it this way, these are kind of the usual Jacobi forms. This is complexification. Because if I complexify, I get the same thing, same global sections where I have the complexified line bond. There's a certain step to go from algebraic to holomorphic, but in this direction, go from algebraic to holomorphic is the easy direction. So that's good. So I get a map. I mean, maybe this was all a bit too many indices and superscripts, but the upshot is I can go from topological Jacobi forms to usual Jacobi forms. Okay. So what I want to do in my final, any questions about this?
So is it a rational isomorphism?
This so the answer is no, but in some cases yes. I mean, this rationally, the problem is there can be, I mean the easiest case, my easiest bilinear form, or the second easiest bilinear form, is I take the 0 bilinear form on Z. The easiest would be the 0 bilinear form on 0. Okay. If I take the 0 bilinear form on Z, then this TGF 0 will be just the untwisted T fixed points of TMF, and this will be TMF plus a 1/4 shift of TMF. But here I will just see the copy of TMF, it's just modular forms, and not the 1/4 shift, because this corresponds to a first cohomology, so it's only H0. So I've given now a long spiel about TJF, but I have not explained how one gets a TMF class from this. So TMF classes. Formed by linear forms. So let B be a bilinear form, and we assume it to be unimodular. Then, so bilinear forms over, maybe I didn't say this, over the integers are actually pretty hard to understand in general. We don't have a complete classification or anything, but it's much easier if we work over the real numbers, as you probably know since your undergrad days. So you get from it a bilinear form BR, R to the D, and we can diagonalize it to get plus ones and minus ones and then I call this number b plus and this number b minus. So, and then there's a theorem I proved together with Negegukov, Leva-Krushkal, and Dupay, namely that in TGFB, a certain shift of TMF, and the shift of TMF is it's 3b minus 2b plus. Maybe it's not so important. The exact shift is maybe not so important, but this is the shift we have. And now we can. And now this equivalence, I don't want to state it's like canonical or something like this. It's a calculation, but in some sense it's nearly canonical because this is up to shift its TMF. So the choice is just up to an invertible element in pi 0 of TMF. Turns out invertible elements in pi 0 of TMF is just plus minus 1. So it's up to a sign, up to a homotopy, it's canonical.
It's even up to a sign for unique.
Sorry?
It's even unique up to sign.
Yes. Yeah, canonical is not a mathematical term, as I've learned during my PhD days. But, but everything which is unique is certainly canonical. Okay, so define TB in, I hope I get it now right, 3b minus TMF as, what do we do? Well, we take this equivalence and then turns out there's a map from TJFB to TMF. How does it work? So TJFB was a global section of a certain line bundle, and with lack of time, maybe I just say quickly. There's something called the zero section of an elliptic curve, and we can get a corresponding zero section from ML to this thing, and the pullback of LB top to this thing is exactly the structure sheaf. And when you contemplate this, you get a map from these global sections of this, the global section of this, so from here to here. And so now here we have an element 1, and this will be sent to TP. Well defined up to sign. Questions about this construction? So now I should give you some information about this thing. Examples. So Q, let's Q be positive definite. Then so we want to say that, so we have now T of the corresponding bilinear form, which sits in pi minus 2 B plus, and B plus in this case it's a QF CD. It's positive definite, so B plus is everything, so I can just write D here. And this maps to minus D. And I want to say that this maps here to the corresponding theta function divided by. This was one of my goals. And I say want because we don't have a complete proof. But the problem we still have is completely on the level of, say, algebraic geometry number theory or something. It's not on the topology side, because essentially one of the problems is I gave this definition of integral Jacobi forms as sections of this LB, and one has to show that this theta function, one defines by concrete formula, actually lifts to this. I mean, it looks integral if you define it, but I mean, you have to prove that kind of Q expansion principle for Jacobi forms. And maybe this is known to somebody. I just didn't talk to the right people, but at least I didn't find the literature, and I didn't find anybody who could explain. Not yet, no. Maybe I should. Yes. So the strategy is clear how one proves it to us, but I mean, this kind of thing about the theta function actually and how it kind of plays with this LB is not quite clear yet. But yeah, I'm pretty optimistic it's true. And then it's further work in progress, which means we have proofs, but it should be double checked so we might look at T of the third simple bilinear form, namely the bilinear form on Z, which is given by the matrix 1. If one does the calculation, then this lifts. Oh, sorry, I want to take -1. Now, that was the positive definite case. Now we take a negative definite case that this equals mu by 3 of TMF. And then let's do something more complicated. This bilinear form, we get eta. And now it's an intriguing question: how many of the interesting torsion elements in TMF you can realize? But unfortunately, I think that at least if we take negative definite things, you might say, "Oh, I have a lot of these." I won't get anything interesting beyond products of mu and eta and so on. But what we might get quite interesting things is if I take something which is not coming from a quadratic form, I have a non-even bilinear form which is positive definite, there one might get some interesting stuff I don't know. So I think this concludes my talk. Thank you very much.
Interpret the fact that the top part of the board defines theta functions associated with bilinear functions or not.
I mean,
I
mean, it might be just 0. I mean, so I think what will happen is that in principle, because the TMF maps further to modular forms, we get for each unimodular bilinear form, we get a theta function. But for example, in this case, you see directly it will be 0 because we only see I project to a 0th cohomology, and this detected in first cohomology. And I think this I would have to double check, but I think something like this will also happen if you have a non-even bilinear form which is positive definite.
Questions?
Can you see that you get 24 delta with delta? Or do you get 24 delta?
Do I get 24 delta? It's an interesting question. One needs. I think probably not. I mean, theta functions are only a small fraction of what modular forms exist. So I mean, they certainly satisfy the constraints they have to satisfy, and that's actually how Hopkins showed that they live to TMF. I mean, we certainly don't get all modular forms which are in the image from TMF. So I don't know whether one gets something like 24 times delta. One can construct it via like a difference of theta functions or something.
So there's this, you talked to us about this conjectural picture about QFTs giving new classes in TMF. There's this construction of like a lattice QFT. And do you suspect that this construction gives you the same element? Or is
Yes.
it
Yes, exactly. So this is like a rigorous construction of something which conjecturally represents lattice QFT on the QFT side. Yes.
More questions? And none online, so we should thank Lennart again for this.